When a car goes around a curve, you feel a force towards the center of the curve, but it's not obvious. Let's draw a circle representing a road, a circular track, okay, like a racetrack, a circular racetrack. So here's our circular racetrack, and here's a car at this position moving along the curve with speed v. Okay? And from our circular motion understanding, we know that if it's moving around this circle, the direction changing acceleration must point inward, and we call it centripetal acceleration, or I'm going to go ahead and use my preferred A sub r, the radial acceleration, which always points radially inward to the center of that circle. So at this location, it's down and to the right, but if the car was over here, it'd be, or sorry, down to the left. If over here, the car was over here, it'd be down to the right, so on and so forth. Okay, now the question we have now is what's causing that? What's causing that acceleration? So the acceleration, we know, is because of the change in direction. It's turning inward, but something has to cause it. Now that we know Newton's second law, something has to cause that. What keeps the car from going straight? And the answer is friction. It's friction on the road. If the road was oily or you hit an icy spot, the car would just keep traveling straight. Okay, so it's friction is pulling the car inward. Okay, so let's now try and analyze that a little more thoroughly with our understanding of free body diagrams and be able to see how that frictional force comes into play. So to do so, we have a top view here. This would be a top view, and we can introduce a translational coordinate or a tangential coordinate, a coordinate that's tangent to the circle, and usually choosing positive to be in the direction of motion, although we don't have to. We have a radial coordinate that's perpendicular to that, always pointing radially inward. And then we'd have like a y coordinate, one that is pointing up and down. Okay, so that one's kind of hard to see. So sometimes it's nice to draw this from, let's say, a side view. So if I'm standing in the center looking at the car, I'd have a side view, and I'd see this car. Here's my car. It's on the road, and looking at it from the side view, I can choose a horizontal and vertical coordinate system. I'm going to choose, since the car is moving this way, I'm going to choose the tangential coordinate to be positive to the left. I'm going to choose my y coordinate to be positive up, and then I can start looking at the forces acting on it. I can see there's a normal force, and so we'll have a normal force pointing up. I see there's a downward force of gravity, and I'm going to show those as the same length, because we'll see in a moment there's no other forces up and down. So since that means there's no acceleration up and down, these two must be equal and opposite. Now, I'm familiar with real life cars that if I take my foot off the gas, the car is going to slow down. Okay, and so there's got to be some sort of friction resisting that car, and we'll go ahead and call it, there's probably resistance in all sorts of ways, but we're going to call it rolling friction. Okay, since the wheels are able to roll, so they're not slipping, it's not kinetic friction, and it's not static in a sense that the car is not sitting there. The car is rolling and slow, and would slow without me pressing on the gas pedals, so there's a rolling friction. Now, depending on what I am doing, I could say that I am coasting or coasting to a stop, so I'm not applying any brakes or gas, and so the car is just slowing under this frictional force, and if that's the case, then my acceleration would be backwards, because the net force would be backwards. Or I could be putting my foot on the brake and applying just enough gas to move at a constant speed, which means there would be a propulsion force, okay, or the engine force, or however you want to call that, but more generally, it's called a propulsion force. And if I'm moving at constant speed, then that propulsion force is just big enough to overcome this frictional force from the rolling of the wheels. Okay, but then if I'm pressing on the gas even more, I might be accelerating forward, which means my propulsion force would be bigger than this frictional force, and I'd have a net force in that direction. Okay. Let's go ahead and just, for simplicity's sake, just choose moving at constant velocity. And so we overall have go F sub p. So we overall, in these coordinates, we have no net force. Now because this is only 2 coordinates, we're not able to see the radial coordinate here. I'm going to be specific and say F net y equals 0 and F net t equals 0. Because I can't say F net equals 0 because I don't know what's happening in the radial direction. So to get that information, I have to draw another picture. I'm going to draw a back view. So as if I'm standing behind the car, staring at the car, and this is the picture I'd see. I'd see the tires on the road, and here's my car, and it's going away from me. So V is into the page, and over here V was to the left. All right. Now I can draw, if we buy a diagram of this, I can still see the y coordinate. I can still see up and down. This time I have a radial coordinate, and if I'm choosing this location, I'm standing from behind, and this is circular track is curving this way, then to the left of me, staring at the back end of the car, is going to be inward. And we're going to just go and call that positive. I'm going to choose to call it positive. I don't have to, but I'm going to choose to call it positive because my acceleration in that component must be pointing inward. That is the requirement of circular motion. So I'm going to use this as my radial component, and the normal force, gravitational force are no different, so this is redundant. I can see both of those. But now the thing that's saying, I have an acceleration in this direction. I know F net R is pointing this way because I know AR is pointing that way. So I have to have another force that's pointing this way. And again, with our logic, if that was ice right ahead, it would just go on straight. It would just go straight off the track. So that means there needs to be some sort of frictional force that's what's keeping it turning. So it's not that the wheels are just turning. It's that the wheels can grab the road through friction, and friction from the road on the car is what's causing it to turn. And that is a static friction. It's not a rolling friction, but a static, because that's keeping the wheels from slipping sideways. So the wheels are moving, the wheels are in the direction of my fingers, my top fingers, and the road is keeping them from slipping. Okay, it wants to turn, and if the friction was there, it would just go straight, and so it's keeping them from sliding off. Okay, so these two free body diagrams now give me all the information. I can indicate F net Y, F net T, F net R, and all these diagrams now give me, I actually have 3 different Newton's second law equations. I have Newton's second law in the tangential coordinate, Newton's second law in the vertical coordinate, and Newton's second law in the radial coordinate. And in this particular case, I can see how the frictional force is related to that radial acceleration. Okay, so just really quick, I'm going to focus on that one. Again, we could do the Newton's second law for the other ones, but for the R direction, I can say, well, I have F net R equals MAR, and AR is special. Okay, I already know that AR is V squared over the radius of the curve. So if the radius of this curve is big R, I know that this direction changing acceleration is V squared over R. Okay, so now what is F net? Well, I only have one force in that direction, and so that's going to be this static frictional force. Okay, and so this is what's causing that acceleration, and this is how big it is. Now a cool question here is you can say, how fast does a car, or what's the maximum speed the car can go with it not slipping off the road? If that was my question, if I'm saying how fast can it go, or what's the maximum speed it can go, that means that this static frictional force isn't just general static frictional force. This is Fs max. And I have an equation for Fs max. So if I'm looking for this maximum velocity that this car can go without slipping, then I can plug in here us times the normal force equals mv max squared over r. Okay. And by looking at my y component, I can see, again, doing the second law for the y, and ay is 0. That means the normal force must equal the gravitational force. Okay, that means I can write this as mu s mg equals mv max squared over r. The masses cancel, and I now can calculate that Vmax is equal to mu s rg all in the square root. Now, I wanted to bring this out. This is very specific to this case, so it's not general. But I wanted to bring this out because we're going to find that this velocity, this critical velocity, which actually has applications to satellite orbits and many other things like roller coaster rides, but it's very much dependent on the radius of the circle and g in many respects. Okay, this came out in a very particular way, so I wouldn't memorize this per se in terms of a general process, general result, but the process gave us that answer. This process can be applied to any problem.